the red areas in the area under the blue, because the red goes past the blue. Do you all see that? Okay, so instead what I'd like for us to do is do this. I'll erase the red here in a second, but I'm going to go, you know how I went up to 1, I went to the right and down? Let's go up and then go over this way and draw my rectangle like that. And then this one go up to 2 over like that, up here, up here, up here. Now look at those black boxes. Aren't they all below the blue? And they'll be below the blue the whole way. So if I take these reds out, like this, then would you agree with this statement? The area of the black boxes added up is smaller than the area underneath the blue curve. Yes? Now, there's a problem here because with the blue curve, the reason why I did the red first is because the blue curve can't come back here. Do y'all agree with that? This blue curve, why can't this blue curve come back here? At 0, it's undefined, so it's asymptotic here, right? So let's just say ignore that one rectangle. Just who cares about that, all right? Just from 1 on, okay? From 1 on, which is really what all that matters, because from 1 on, that's when our series starts, right? So if we look from 1 on, the area of the black boxes added up is less than the area underneath the blue curve. Now, what is the width of all of these? 1, 1, 1. So this is 1 wide, and how tall was this one? This was this one right here was 1, but we went to this one was 1/2. So the area of that's 1/2, right? 1 times 1/2. This one right here is 1/3, 1/4, 1/5, 1/6. Do y'all see that? So if I asked you to add up these areas, 1/2 plus 1/3, isn't that the same as saying that series? So this series right here is represented by the area of all these black boxes. Do you agree with this statement then? Do you agree with that? Mm-hmm. Right? That's what I just said. The area underneath that function between 1 to infinity should be bigger than the sum of all these boxes. Now, what if this converges? What if we do this integral and it converges? Then if that goes to a number and this has to be smaller than or equal to a number, then this must converge also. Now, do they converge to the same thing? No. But if this goes to a number, this has to, because this one's bigger than that one. And this is what the integral test is saying. This is on your sheet. Look at the integral test there. It says there that let's say you have a series, right? I'll explain all the other little ancillary things in a second, but it says say you have a series. Then it says that if the integral from 1 to infinity of f of x dx converges, right? It says if this thing converges, then so does that. And the integral test also, amazingly, and we don't have to worry about this, I'm not going to prove it to you, but the integral test also says that if this integral diverges, the series also diverges. That's a little harder to show visually. But this is the result of the integral test. So do you all see how we can use this? You see how, so look, I'm going to show you right now that a harmonic series diverges. I'm going to prove it to you with the integral test. I'm going to do it real quick, and then we've got some other things we need to talk about with integral test, but I just want to kind of set it up for you to see how this would work. If we're trying to do this right here, then what I could do is take a look at this integral. And we all are very comfortable with the antiderivative of 1 over x, right? That's just natural log, absolute value of x, and we're evaluating this at two endpoints. Now we have infinity, don't we? So technically this is an improper integral, so we're supposed to do like the limit, right? And then do like t goes to infinity and replace that with t. But because we've done that already, I'm just going to leave it as infinity and not use a limit, and we're just going to do the limit in our head. So what happens first? We try and plug infinity in here. So what does the natural log function do as you go out to infinity? It becomes infinite. So we know that we get infinity when we plug in infinity, and then minus, and then when we plug in 1, natural log of 1 is 0. So this becomes infinite, doesn't it? Which means it diverges, right? The integral diverges. And according to the integral test, if the integral diverges, the series diverges. So our conclusion would be that this diverges from integral test. Does that seem pretty nice? That seem pretty straightforward?
So when we're testing a series, would it be wrong to go from like the nth term to testing it by integral?
If you look at the series and you feel like you want to integrate it, then yes. Like go from the nth term test straight to the integral test. Usually the series itself will indicate to you what to do. Like you look at it, you're like, yeah, I know how to integrate that. I could do that, you know? Okay, so now I left out some details because I just wanted you to see how it would work real quickly. But technically I've left out a bunch of stuff, and if you did that on a test, you would get like 2 points out of 10, all right? Because I would like for you to read to the side what this little comments are. What does it say about this function f? Because we are using this function right here as our f of x, right? That's kind of what we're looking at, that sequence 1 over n, and we're saying to ourselves, oh, that looks a lot like 1 over x, right? So what does it say about that function? Must be continuous. Okay, what does continuous mean? Basically no holes, no discontinuities, no places where it's undefined, right? Now, that function, 1 over x, is it continuous? Not at 0, right? Not at 0. But we're only going to be looking between where and where? 1 to infinity. So is it continuous on the interval 1 infinity? Yes. Okay. So far, this function qualifies for the integral test. What else does it need? It needs to be positive. So what does it mean that it has to be positive? Okay, so I'm going to start writing these conditions down. To use integral test, here's what we needed. First, f of x equals 1 over x. I'm using this specific example. Must be continuous on 1 infinity, which it is, only discontinuous at x equals 0. Okay, so I'm kind of like writing this out. And this is what you would have to do on a test. You can't just go start doing the integral test. You have to satisfy all these conditions first. So you have to show this. So this would be what I would want to see. You say, all right, this must be continuous on this interval, but it's only discontinuous at 0, so I'm good to go. Now, next thing I need to show, f of x must be positive on the interval 1 to infinity. So is it? Well, 1 over x, right? I mean, that's a positive number. And if I'm going to be plugging in x, and x has to come from here, then that has to be a positive number, right? And the ratio of two positive numbers is positive. So it is a positive function, yes.
For that first part, if n is starting at like 3 to infinity, or are we always
Yeah,
going to be
yes. If the original sum was n equals 3 to infinity, then your integral would need to go from 3 to infinity. So yeah, I'm only saying 1 to infinity because my original series started at 1. Okay, so I have 2 of the conditions satisfied. What about the third condition? Must be what? What must be decreasing? The function, right? F of x must be decreasing. Ooh, this one might not be as easy to show. Unless we remember some stuff. How can you show a function is decreasing?
You show that it's less than the function plugged in with the high, or plus 1.
Okay, so like I think what you're thinking is, remember with the sequence? With sequences, to show a sequence decreases means to show that this one is bigger than the next one, right? That means they're getting smaller as we go. That's easy to do with sequences because these are nice integers. So it's easy to show decreasing with the sequence. But how do you show a function is decreasing?
Would it be function plus someone?
I'll give you a hint. You're going to have to use some knowledge of Cal 1. The derivative, it has to do with the derivative.
Set to 0?
No. The derivative set to 0 is where your function is flat. I want to know where your function, whether or not your function is going down or not, right? Yes. Where's the derivative negative? Look, if I say, in Cal 1 or even in here, if I say, hey, look, everyone, there's this function that when you take its derivative, the derivative is negative, then you can tell me that that function is decreasing. Because negative derivative means you're going down, right, from left to right? So what I need to do here, what you need to do for this step, is to show me that the derivative is negative on this interval. It's going to be pretty easy to show. So I want to show f prime of x is less than 0 on the interval 1 infinity. Understand that? We want to know, we want to be able to verify that our derivative is negative. That would mean our graph is going to be going down. Remember, we need this condition, don't we? Like, think about your sequence. Doesn't your sequence have to go to 0? Your sequence. The dots have to go to 0? Well, the function must also go to 0 then. So we need to verify it. So what is the derivative of this function? The derivative of 1 over x, not the antiderivative. This is the same as x to the negative 1, right? Take derivative. This is negative x to the negative 2, which is negative 1 over x squared. That's a derivative of our function, right? And when we look at this, the numerator is negative, right? Always. And the denominator is some number squared, which is always positive. And the ratio of a negative over a positive is always going to be negative. So this is a negative number, which checks off. My derivative is negative. I didn't tell y'all about my old office mate in the function, the love function. I did?
No, I didn't hear that.
Was it in here or no? It wasn't in here. It must have been last semester. I'll make it real quick. One of my colleagues, when I first started teaching here, he was really, I didn't like the guy, and he no longer teaches here, but he was telling me about how he had told his girlfriend, and we're all math dorks in the math department, like, you know, this is not too crazy, but he said that the derivative of, he told his girlfriend or something that the derivative of his love function for her is always positive. Oh, exactly. That's the effect he wanted. So if this is time and this is the love, however you want to define that. Well, so his idea was this, that the function that graphed love versus time, the derivative was always positive. So we'll call it, let's say, L, capital L of x, right? The love function. The derivative of this is always positive, which meant that it was increasing, right? I think what he was trying to imply was that his love was growing without bound, right? But then I shut that down pretty quick because it is possible to have a horizontal asymptote and still have a positive derivative all the time. So this is asymptotically approaching that value. It is increasing because you can get closer to something without ever getting there, but it can still be bounded above. Yeah. So I added another condition, which made it always have to, like, to get it fixed, because it wasn't quite enough. This wasn't quite enough. He needed to add a little bit more to that condition.
So he said this and you were like, no.
Yeah, I was like, I know what you mean, but yeah, no. You could have I think I just said you could have a horizontal asymptote. You could still have a horizontal asymptote. I gave him an example of a function that does that, and then he's like, yeah, you're right. I need to tighten that up a little bit. All right. She probably had no idea what he was talking about. All right, here we go. All right, let's start running through things. Nth term test. Nth term test. Take that, take the limit of it as n goes to infinity. You get infinity over infinity. You'll have to switch it to a function of x, do L'Hopital's rule. Do L'Hopital's rule, you're going to get 0. Nth term test is going to fail. Geometric series? No. Not, it's, the n is not up in the exponent. So not geometric. Harmonic? Constant over linear? Nope. Yep, nonlinear on the bottom. Not harmonic. Telescopic. Well, how did we go about the telescopic problem that I gave you earlier? We did partial fraction decomposition, didn't we? And the problem here is that we can't do partial fraction decomposition because the denominator is irreducible. It's not factorable. So we have an irreducible quadratic. And if you go back to partial fractions, when you have an irreducible quadratic, your whole goal, like if you have a quadratic down here that cannot be factored, then up here is going to be, we are going to try and find a linear expression in x on top. That's the goal. And we already have it. We have a linear expression in n over an irreducible quadratic. So if you tried partial fractions, you would actually circle yourself back to this and be there. So that's not going to work. So it's probably not telescopic. Well, there's only one thing left, right? Integral test. What would the function be that we have to look at here? X over x squared plus 1. Do you have any hesitations about integrating that? U sub, what's the basic U sub?
X squared plus 1.
X squared plus 1 is U. The derivative of that is 2x. You're off by a constant, big deal, right? So we'll be able to integrate that. Right? Okay, so I don't mind integrating that, but I need to show that it meets all the criteria. So first thing, I must show f is continuous on 1 infinity. Now, is it? Is this function ever undefined? No, right? There are no discontinuities here. So one thing I could say here is, x squared plus 1 can never be equal to 0, right? That's not possible. So check, this is continuous. This function is very well behaved. It's better, this one behaves better than even 1 over x, right? 1 over x had a discontinuity at 0. Didn't matter to us, but, all right, so that's all I have to show there. Now, I need to show f is positive on 1 infinity. So when I show it's positive, how do I do that? Take a look at this. Well, the denominator is always positive, right? We don't care. I mean, square something, add 1, it's positive. What about the numerator? That's always positive. Why? Yeah, the domain restriction, 1 to infinity. So the x I'm plugging in here has got to be positive. So this is good, right? And the third and usually the hardest thing before integration is to show that f is decreasing. I suppose your love function could have a negative slope, but that doesn't mean it's the end of the world. I mean, because you could have an asymptote on the bottom, so you could have like a minimum amount of love over time. So, right? Isn't that sweet? It's not quite February. It's not Valentine's yet. Okay, decreasing. So how do I show it's decreasing? I take a look at its derivative, right? And that, when I take the derivative, I'm going to have to use quotient rule. All right, so however you do it, I mean, it's taught different ways. We should all get the same thing at the end of the day, though. So that's your quotient rule. Derivative of the top one times the bottom minus derivative of the bottom times the top over the bottom squared, or Lodi high, that whole thing, yeah. Lodi high minus Heidi low.
Square the bottom of the way to go.
Square the bottom, way to go. Really? I didn't know that part. I feel like I should be dancing while I'm singing that. Okay, so what do we get on top? X squared plus 1 minus 2x squared all over x squared plus 1 squared. Now the bottom is positive, right? There's like no, we don't even need to consider that. But we'll keep it there. 1 minus x squared. And then x squared plus 1 squared. Now, I do have a little bit of an issue here. All I need to show is that that numerator is negative, right? But at 1, what's the numerator? Because remember, we're going 1 to infinity? At 1, isn't the numerator 0? Well, that means that the slope of your tangent line is flat at 1, right? At 1. That's okay, because we need the function to be decreasing. So what we know is that if you were to graph this function, when you're at 1, I don't know where is it at 1? It's actually like, I don't know, maybe it's doing this. I'm not sure, but it's a flat tangent line. We just need to show that as we move on, it's going to decrease. So from 1 on, can we guarantee that this is negative? Yes, because when I take a number bigger than 1 here and square it, that's going to be bigger than 1. And then when I do 1 minus that, it's going to be negative. So this is negative. So this works. That's negative. It checks. If this function was not decreasing, then you can't use the integral test. So you got to move on to something else. So now the integral. And remember that whatever we get for the integral, whatever that answer is the result for this series. So here comes the integral. Integrating x over x squared plus 1 dx, making a substitution. U is x squared plus 1. Du is 2x dx. 1/2 du is x dx. So this is a basic u sub, so I'm going to go quickly through this. This integral becomes 1/2 1 over u du. So that's what happens when I do the substitution. And this gives me 1/2 natural log of u plus c, right? What's u, though? X squared plus 1. Okay, so that's my antiderivative. I'm not done. That's just me getting the antiderivative. Now I need to actually do the work here. So if I want to do the integral from 1 to infinity of x over x squared plus 1 dx, I know that this is going to become 1/2 natural log of x squared plus 1, and then evaluated 1 and infinity, like that. So I just did this just to get my antiderivative, and then I came back over here to actually evaluate. And what happens when you plug in infinity? You get infinity, right? This becomes infinite, and then natural log of infinity is infinity, so we get infinity. And then we get minus. Now plug in 1. Natural log of 2 times 1/2, who cares, right? It's a number. This is just a number. It's a fixed constant. So this is infinite, which means it diverges, right? It diverges. So this diverges by the integral test. How do y'all feel about that? All right?
So
Okay.
are you okay with this? Kind of like skipping the whole limit to t?
Yes. Now, yes, when I teach this, when we're first teaching this, I do, t here, and then I do limit, right? T goes to infinity.
Yeah.
But most of the time as we progress into more math courses, if you've seen improper integral, they will actually do they'll do the infinity here, and then maybe they'll do natural log of infinity. They'll actually write that in on the next step, and it's an idea. It's a limit that you're doing mentally. All right, so this leads us to one more result that we can come up with today, which is going to be kind of nice, and that is this idea of a p-series. Now that's harmonic, right? That's harmonic? Okay, so let's say we have n, but this time we raise it to a p. P is like the power, okay? So what if we have n to a power? So I'm going to give you a couple of examples of this. 1 over n squared. 1 over n cubed. 1 over the square root of n. 1 over the cube root of n. Those are all examples of p-series. What's p in this case? P here, 3, p here, a half, p here, 1/3, and so on and so forth, right? These are all examples of what we call p-series. Every single one of these could be done using the function 1 over here x squared, here the function 1 over x cubed, this one 1 over the square root of x, and then this one 1 over the cube root of x, right? I could do for each of these an integral test. And I could show this is continuous, this is positive, this is decreasing, continuous, positive, decreasing, continuous, positive, decreasing. And I'm not going to go through it, all right? But you could do that for each of these. And what we would discover is that this series will converge if p is bigger than 1 and diverge if the absolute value, or p is less than or equal to 1. Now this is on your sheet. Do y'all see that here? P-series? Do y'all remember that extra credit assignment that I gave to integrate 1 over x to the p? Right, some of y'all did it. You could actually use that extra credit assignment to show that what we could do is take a look at the integral from 1 to infinity of 1 over x to the p. And this integral right here converges if p is bigger than 1 and diverges if p is less than or equal to 1. So I'm not going to show that because of time. That was a bonus question. So if you did that bonus question, if you did it right, then you've already shown that this would work. All right, so we are now going to just take this kind of on faith. You believe me on this? So if we see a p-series, then we can draw the conclusion right away. All right? It has to be, though, well, this could be any number because it's a constant, could come out, all right? But this has to be only, yes, but this has to be n to the p. You can't have more stuff down here. Like you can't have n squared minus 2n, like that one we did with telescopic. That's not a p-series because you have two terms in the denominator. It has to be a single term. Yes?
So like for the 1 over root n, if it were like 2 over root n, could we pull out the 2?
The 2 would not matter. It would still diverge.
Okay.
Yes. Because all you're doing, constants can come out of sums regardless of what they do. Just like constants can come out of integrals, regardless. Because if every single one of these terms in your series has a common factor in it, you can always pull that out, regardless of what the sum does. Is that, yeah? Okay. I'm curious, I just want to ask you a question here, and this will actually lead us to a little result here. I want to know, does this converge or diverge, everyone? Does that converge or diverge? It converges. Do you know what it converges to? No, right? Because it's a p-series, all we know is it converges, right? It's not telescopic and it's not geometric. So that's convergent. Is this convergent? So the difference between these two is that this one starts out, you know, like 1 plus 1 over 2 to the 10th plus 1 over, 3 to the 10th plus blah, 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 right? And we're saying that converges. This one starts out way down the line, doesn't it? Okay, the answer is that they both still converge. The only difference between these two is about 100,000 terms difference, right? Just 100,000 term difference. A finite number of terms has zero impact on the convergence or divergence of a series. Follow me? I'll say it again. A finite number of terms has no impact on the convergence or divergence of a series. So if this thing converges, then starting further out in the series still converges. All right? If this diverged, like let's say that was like, you know, square root of n, this would still diverge. All right? A finite number of terms has no impact on convergence or divergence. All right, 1031. I think this is probably a good place to stop. We haven't done comparison. Nope, we still need to do comparison. So we are not completely done with 8.3, but we don't have really time to get into it right now. So we'll come back on Wednesday. I know Wednesday's a day before Thanksgiving. You know, I want to talk about the grades. I will be here on Wednesday. I cannot cancel class. I'm not